My name is Bernard Scheider. I will talk about swak4Foam and PyFoam, and I will give you an introduction about the two of them. And I'll try to do all the slides at a time. Sorry, one more. So, okay, sorry, I had to go through this. Okay, at first, let me talk about this presentation. This presentation is about two programming libraries and toolkits, PyFoam and swak4Foam, which were mainly developed by me. They both use OpenFOAM. They complement each other quite nicely. So I can't, so when I give an introduction, then I'm doing an introduction on both of them at the same time. Yeah, the intended audience for this talk is basically you, hopefully, but in general, it's people who all worked a bit with OpenFOAM. Worked a bit means you've been through the tutorials and set up a case on your own, and you don't have to know anything about PyFoam and swak4Foam except that they exist. The aim of this presentation is to enable you to start using the two of them. There is no programming that happens here. There are training files provided. When I talk about hands-on in this session, there won't be hands-on, but you should be able to do everything in this training on your own computer. We will use a standard tutorial case. As I said, it's now that I've had all these problems, it's less than 1.5 hours. I will have to speed through some things. If you have questions about the training material when you work through it, please feel free to contact me. So I'm going to go through this quickly. As I said, I'm Bernard Scheider. I've developed swak4Foam, PyFoam, and another package that is not related to this. It's Ansible Foam installation, which is, I call it the universal build script for OpenFOAM. My real work is I work at a small consulting company called HFD, which is Heinemann Fluid Dynamics, which is we do all kinds of stuff, mainly developing fluid simulators based on OpenFOAM and other software. We are working with PyFoam. PyFoam is a library, and it's also a collection of utilities based on this library. It was written in Python. It was designed to have very few dependencies. Basically, you only need one external Python library, NumPy. All the other stuff it installs with it. And it is completely OpenFOAM installation agnostic. It only looks at OpenFOAM cases from the outside. It does case manipulation, running simulations, and looking at the results. Once you have installed it, all the utilities start with PyFoam. So if you have a decent shell, then with tab completion, you get a full list of all the commands that are there. And all the utilities have an help option where all the documentation is located. swak4Foam is, the name swak4Foam stands for Swiss Army Knife for Foam. Like a Swiss Army knife, it's useful in a lot of situations, but it's rarely is the best tool for any task. But sometimes it's more convenient to get Swiss Army knife than to fetch a chainsaw to do some little woodwork. So it's a result of some utility. It's the merge of some utilities that I've written before. The goal of swak4Foam is to make the usage of C++ unnecessary if you want to do complex boundary condition, initial conditions, or evaluations. The advantage of this is that, So the core of swak4Foam is it's a collection of utilities or parsers. A parser is basically a little program that looks into a textual input by the user and interprets it. So it interprets, for instance, t minus 273. It interprets it like take a field t, which is usually the temperature, and subtract this value from it, and then do whatever you want with this value. You can have these expressions you can have on different types. You can have them on internal fields, on boundary fields, but also on subsets of your mesh like face sets, cell zones, and so on. And there's a bunch of utilities, some of which we are going to touch on here. And yeah, it tries to reduce the use for the need for throwaway C++ programs. In the beginning, if you wanted to do something more complicated, like having a non-homogeneous initial condition, then you had to write your own C++ program, which only worked for that particular case, and then you had to throw it away. Yeah, before we start, there's going to be some command line examples in there. Usually they look like this. It's a smaller sign and then what you enter. If it's a longer example, then it looks the way it looks down here. In blue is the stuff that you typed, and in black is the output by the machine. And if the line is too long, then there is this book and cont, but that means basically all that is in one line. For this, I will do this with OpenFOAM 8.0, but older versions work as well. Other forks like Foam Extend and Foam 2012 should also work. But I took the foundation release because there is one nice boundary condition that is in the ESI fork is missing, and I'm going to re-implement that later to demonstrate how Groovy BC can be used. I prepared a Docker image with a pre-installed PyFoam and swak4Foam so that you don't have to reinstall it to do it. Yeah, it has the most recent PyFoam installed, it has the most recent swak4Foam installed, and it's based on Ubuntu 18.0. The image is over 2 GB. If you want to use it, you have to have a machine that has Docker installed, and you just type docker pull and you get the whole machine. Then what you have to get is a special script that I use for these Docker images to be convenient. You have to get the script from this URL and save it as run container. And then once you've made it executable, then you can, with run container and the name of the Docker container, this will pull the Docker container and start you into a shell. That will look basically like this. If you run the script without any arguments, then you get a list of all the images that are compatible with this script. You get them installed. Once you run the script, you are inside of the Docker container, and OpenFOAM and swak4Foam and PyFoam are accessible to you, and you can just start typing the stuff. And the examples are also found either in you find them in the Docker container in the root directory examples. There are 4 subdirectories. Each of these holds one stage of this presentation. You can also get the tarball with the examples from the OpenFOAM wiki. The first thing, I think I skipped this. Basically, this presentation follows Ignaz Gartenschirl. Ignaz Gartenschirl is a CFD consultant, and he is working at a company named Hot Rooms and no, Warm Rooms. It's Warm Rooms. And what he wants to do is he wants to simulate the heating of a room with a moving oven, which is a interesting concept. And he is very fond of PyFoam and swak4Foam, and therefore will try to do all this with PyFoam and swak4Foam. The first thing he usually knows is he says, okay, at first I'm going to check whether PyFoam is the correct version. That's PyFoam version. This gives you a lot of output. Down here you see the currently installed PyFoam version. Basically, with that output, if you have a problem with PyFoam and you think you want to report a bug to me, then use this utility, and this basically gives me all the information about your machine, about installed OpenFOAM versions, which Python version you have, and things like this that help to debug the problem. Then Ignaz wants to make sure that swak4Foam is working, and the easiest way to make sure that it's working is basically just run funky set fields. Then funky set fields will start. It will end with an error message. But down here you see the swak version and the release date of that swak version. So that is also a way to make sure that you have the latest version of swak4Foam. The first thing is basically, as I said, Ignaz is working at Warm Rooms Limited. It's a small company, and they want to innovate the way people heat their houses. And to do that, they use moving ovens. And they say, okay, you're new in the company, please just simulate a simple cabin. And Ignaz remembers, okay, I don't even have to mesh. There's a tutorial case in OpenFOAM that I might use, the hot room case. So at first what he does is he starts his first PyFoam utility. That is PyFoam clone case, which only copies the parts of a case that are necessary to start it. So that's the system directory, the constant directory, and the zero directory. And the first thing Ignaz usually does is that because of another utility, he moves the zero directory to zero.org to avoid overwriting any stuff there. So that's what you see here. And what you also see is that PyFoam creates some files. It creates a file with the name of the case and .foam. So that file is basically, that's empty. It's just so that you can open Paraview, open this file and start post-processing. And what it also does is it creates a file PyFoam history. In that file, PyFoam records every command that every PyFoam command that you've issued, which makes it easier to see what you did in this case and how you prepared it, especially if you come back from vacation and after 3 weeks and you don't remember what you did. You look at the last lines of the PyFoam history case and you know, okay, I did initialize the case in this way, for instance. So Ignaz is, some call it lazy, others call him efficient. He tries to avoid repetitive work. So he wants to the other thing with being lazy and efficient is if you optimize your stuff, then you don't forget anything during setting up. And what he does is he uses a utility PyFoam prepare case. That utility can do a lot of stuff where I'm only going to touch on the top of that. At another workshop, I did a complete presentation only on that utility and what to do with that utility. So he starts PyFoam prepare case. PyFoam prepare case prints out some stuff. Then it says, okay, he's looking for template files, and that's the more advanced stuff. What it also does is it writes out some stuff. No, it runs block mesh automatically if it finds a block mesh dict, and if there is no other indication for it how it should create its mesh. If it finds a appropriate script, then it runs that as well to set, for instance, initial conditions. And if it finds a set fields dict and it doesn't find a script for setting initial conditions, then it also runs set fields automatically. So basically, for the most simple tutorial cases, it does the same thing that all run would do. So the next thing that Ignaz does is he starts the most used utility in PyFoam. He starts PyFoam plot runner. PyFoam plot runner is a utility that basically recognizes that it's run inside of an OpenFOAM case. It starts the solver, it gathers the output of the solver, it analyzes the output of the solver, and it plots these results. It also does some other things. For instance, what it does here is when I say clear, then it removes any results except for the initial condition, except for the zero directory. Progress is what it does here is it says, okay, I will gather the results, but I won't print them directly to the terminal. I will only print the current time, like you see it in the last line down here. Auto is something quite nice where it says, okay, it looks for processor directories, and if it finds processor directories, then it will automatically run the case in parallel. So it will prepend NPI run and the necessary options. And hard copy and prefix, these belong together. I will show you that down here. Another nice thing that the PyFoam runner utility does is if you write auto, you don't either you write the solver that you want to use. For instance, you write simple foam, or you write auto. If you write auto, then PyFoam looks into the control dict. In the control dict looks for the solver that is specified there, and then it uses that solver, and it tells you about it here. For instance, it looks into the control dict and says, okay, that is a case that is supposed to be run with OpenFOAM, and it runs it. And after you started, a number of windows pop up, and you see some plots. You see plots of the residuals and other things. And once it finishes, for instance, here that the case finished after 2000 seconds, then you see the usual results that you used to see in an OpenFOAM case, and then there's a couple of stuff that PyFoam added. For instance, here it says here the PyFoam runner OpenFOAM log file. That's basically the output of the solver, so you can still look at the output of the solver. In the analyzed directory, it wrote all the stuff that it like residuals that it found during running. So yeah, that's what I explained here. So basically, that's one of the things. That's, for instance, that's a plot of the residuals of the linear solvers that you see. That is updated during the running. The continuity is plotted. And one thing that, for instance, Ignaz ran the case, then it was evening, he went home, he shut down his computer, and when he came back, for instance, he wants to look at the curves again, and he doesn't want to rerun the case, so he just wants to replay the results. So there's a utility for that, that's called PyFoam Plot Watcher. You tell PyFoam Plot Watcher, you tell it, okay, here is a text file. This text file is the output of an OpenFOAM run. Please analyze it and do all the usual plotting. The text file can even still be, let's say, alive. So for instance, if this text file is the output that the queuing system does for a simulation of yours, then it follows that log file, and if there is new output to the log file, it analyzes this as well and updates the curves. So you can, instead so it's not necessary that the output file is from PyFoam. It just has to be a proper output for a OpenFOAM case. Also, with hard copy, what it does here is it plots the plots, but it plots the plots on your screen. But if you need the plots for some reason to insert into a presentation or something like this, then you can tell it hard copy, and with prefix you can add a name to these things. And what you see then here is that it creates, after it finished, it creates a number of bitmaps, and you can insert these bitmaps into your whatever. Yeah, here's, for instance, that's the number of iterations, execution time, and the Kuro number. Okay. So the next thing Ignaz wants to do is that's the basic tutorial case that he used. He wants to do some visualizations to judge improvements of the heatings. At first, Ignaz doesn't like mouse clicking too much, so he wants to automatize this Paraview clicking. And also another thing is he wants to be sure that he also always uses the exactly same perspective, the exactly same filters as he used, that he produces basically the same perspective for every run. And for that, a very nice thing in Paraview helps him. That's state files. If you haven't used state files in Paraview before, do it. It's quite nice. It's basically what you do is you load your data, you do a complicated visualization, and then before you finish, you say save state, and this will save a special file. And what you do is you close the Paraview file, then you open Paraview, press load state, select the state file, and Paraview will ask you, this is not the case the state file was created for, which case do you want to use instead? Then you click to that, and then you have exactly the same visualization. The only thing is that basically the case has to have the same boundaries and have the same size for this to work. But this can be done even easier or even more flexible. Basically, what Ignaz does here, he prepares a visualization in Paraview. He uses a threshold filter here down here to find out where the very hot zone is. He uses streamline filter to generate some streamlines. Then he adds the time, and down here he adds a text. And what he does here is he adds a special string % case name S, and then he saves this. And Then he uses a utility that's called PyFoam snapshot, that needs three information. It needs the name of a state file, it needs the case, and it needs to be told which times do you want to do these snapshots of. And what it does is it gets the state file, it manipulates the state file so that it points to the current case. It loads a GUI-less version of Paraview, generates the screenshots, and then finishes. So basically you don't have to touch the mouse, you just generate the pictures. And that way you can be sure that they look exactly the same. So the calling of this looks like PyFoam snapshot, the point for the current case. Then this is a state file that comes with the example files. And then we tell him, okay, take the time 200 and take the latest time. And then it generates two files, one for the time 200 and one for the latest time, which is 2000. This doesn't work with the Docker container because there's no Paraview in Docker container. And the nice thing is that you see that the case name that we specified before is now replaced with the case name that you have. So basically what you have is if you use that, you have automatically labeled plots where you see, okay, this is data from this case and this time. And yeah, this is how it looks in the end when the state is almost steady. Sometimes you just open Paraview to look at the numbers of the case, and if you just want to know, okay, what is the maximum temperature, for instance, in this case, then there's a utility in swak4Foam that's called field report. You just have to tell field report the time or the times that you want to do this, and you've got to tell it which field. For instance, you say, okay, I want to know about the temperature and the time 200, then field reports runs, loads this field from disk, tells you about the size. So the size is basically the number of cells. It tells you about the volume of the case. It tells you, about the minimum and the maximum, the average. Some of these outputs don't make any sense for that value. For instance, the sum of the temperature or the weighted sum, or the volume weighted sum of the temperature don't make much sense. But the average and the volume weighted average, they make sense and can be interesting information. What it also does is it calculates the median for you. You can also tell this utility to do additional stuff. For instance, if you say do boundary, then it will write out information about the boundary fields, so you can get the wall temperatures quickly as well. And if you tell it to write it to its CSV file, then it generates a CSV file for you, which you can immediately get into Excel if you think that these numbers are sufficient for your analysis. So now he ran the case. That's a vanilla tutorial case. Ignaz wants to throw away all the stuff. So he uses PyFoam clear case. That's the same thing as the clear option for the runner. So it throws away all the non-essential stuff. And you can tell it to keep certain stuff. For instance, if you say keep last, then it will keep the last time step, so the directory 2000 as well. And if you say verbose clear, then it will tell you what stuff it threw away. Similar utilities, for instance, PyFoam pack case, that basically takes all the essential files and packs them into a tar file. If you, for instance, if you want to pack your case together to send it to somebody else to make for replication, for support, for whatever. Okay, so that's starting with PyFoam, and the next thing is using swak4Foam, using expressions. The set fields utility is nice, but it's not very flexible. Basically, all you can do is either set a homogeneous boundary, homogeneous initial condition, or you can set a box. There is a utility in swak4Foam that was the oldest utility in swak4Foam that existed before swak4Foam, that's called funky set fields. The idea of funky set fields is that the user writes an expression and the utility creates a field with that value. And there's a number of options to that. I'm going to explain it to you here. For instance, if 300 Kelvin, it's quite easy to tell that 300 Kelvins, you subtract 273 and you've got Celsius, so you've got a pretty good feeling whether this is warm or not. But for people who use Fahrenheit, that's not so easy. So for instance, what you can do with funky set fields is you say, okay, for all times starting with 0, create a field that is called temperature T Fahrenheit, and the content of this field should be an expression. The expression is the content of the temperature field times 9/5 minus this value, and that's supposed to convert it into Fahrenheit. So basically you can run this utility and then you can use T Fahrenheit, for instance, for post-processing in Paraview, or you use field report to see how warm the room would be in Fahrenheit. So basically the temperatures we had before, 301 degree, if I remember it correctly, that's 81 to 82 degrees Fahrenheit. There was also a way how that's the set fields directory was used to do the heater on the bottom of the case. It basically specified a box. It's in that box, it set the temperature to 600, and then it cleared all the interior field and just left the boundary field, and that way it set the temperature. Now, Ignaz wants to do it similarly, but he wants to do it with funky set fields. And with funky set fields, at first it looks a bit more elaborate, but it's in the end it's more flexible that way. So what he says is, okay, take the field T, not create, take the field T, keep the patches, which means, okay, keep the patch information, please keep it. And now set an expression 600, but don't set this expression everywhere. Only set the expression where this condition is true. And this condition is, that's a bit more complicated. That basically says, okay, get the position and the X value. If the X value is bigger than 4.5, and this is how end is written, logical end is written in C++. And if the position is smaller than 5.5, and do the same for the set position, only in these cases set it to 600. So he runs funky set fields. And yeah, and what you get is this column of fire. So basically it writes a 600 degree, yeah. This is the region where you have 600 degree Kelvin. The syntax of swak4Foam expressions is quite similar to the syntax of C++. The usual operators are there. And it uses special operators like AND for the inner product and this head operator for the same for the outer product. That is the same as OpenFOAM would use it. Okay. So we don't want this column of fire. So what Ignatz then does is it does funky set fields. Now it says keep the patches, use the field T and set the expression to 300. And because we set the field on the patch to 600 with the value patches option in the previous command, it now does exactly the same thing. So as I said, it's easy to forget setting up such things when you don't do it automatically. So what Ignatz usually does is he creates a shell script, case setup. That shell script is automatically found by PyFoam prepare case after it created the mesh, and it will be executed. And that way, if you use PyFoam prepare case, you can set up the case with the initial conditions that you want. It's basically, he just copies the last two commands to this script, and when he runs PyFoam prepare case, the script is automatically executed. So now he says, okay, it's nice that I get the residuals plotted during the run, but it also would be nice, for instance, to see the temperature extremes during the run. What he does is he lets swak4Foam get these values, and PyFoam will then analyze it. For that, we use a function object. I don't know if you have used function objects before. Function objects are basically small plugins that you specify in the control dict and which are executed at the end of every time step. So there's a lot of function objects inside OpenFOAM that calculate wall heat flux and things like this. And there's also a lot of function objects in swak4Foam. To make sure that these function objects are found, you've got to add this libs entry to the control dict. This will load this library once the solver starts, and once this library is loaded, OpenFOAM knows about these function objects. And function objects are specified inside of this functions dictionary, also inside of the control dict. Every function object is a dictionary. At first you need a name, and you need a dictionary specifying which function object to use and what parameters to use. So you use the types, you specify the type. That's, for instance, here we use swak expression. That's the most versatile of the swak4Foam function objects. You specify an expression. You say, okay, I want to evaluate this. The expression here is quite simple. It says, okay, take the temperature. Then you've got to tell it where you want to calculate the temperature. Here we say the internal field, but you could also use patches. You could use cell sets, cell zones, yeah, whatever. And then it says, okay, verbose means, okay, and the results of your analysis, not only write them to a file, but also write them to the screen or to the console. And you'd say, okay, but 4,000 temperature values that I don't want to write them to the console. So you've got to specify what statistics you want to have about these files, about the temperature field. So the obvious candidates would be minimum and maximum. And usually you want to use the average. In swak4Foam, there's either you use average, that would be That would be a plain average of all the cell values without a weight. With weighted average, it uses the cell volume as the weight. So basically, small cells don't contribute as much to the average as big cells do. So usually you use that because it's more correct. And what I like then is weighted quantile 0.1. This basically says it looks at the temperature values and says, okay, give me the temperature where 10% of my volume have a lower temperature than this temperature, and also weighted quantile of 90%, which basically means, okay, 90% of the temperature are lower than this. Basically, what I like to use these because they are a bit more stable. If there is a single cell that has a very extreme temperature, then if you use a weighted quantile of 0.99, for instance, then this cell is thrown away and you get a more reliable result. Okay. So basically, if you add this function object, and if you now run with PyFoam runner, which is basically PyFoam plot runner, but without the plotting, if you run this, then in addition to the regular OpenFOAM output, you now get this output expression temperatures, and it writes, okay, the minimum, the weighted quantile, weighted average, weighted quantile 90%, and the maximum. And that's nice, that's a lot of numbers, but we want to see pictures. And for that, you can use PyFoam, because PyFoam already does analyzing the output. You just have to tell it, here I have my own custom expression. And for that, you use the custom regex file. If PyFoam finds such a custom regex file inside of the case, it automatically loads the expressions and uses these expressions to analyze the output. For that, it uses regular expressions. I think, as we're a bit late, we're going to skip the details of regular expressions. On the next slide, I've given you a simple introduction. All you need to know about regular expressions. And so, for instance, to scan for the temperature, what you prepare it. The custom regex file has the same syntax as a regular OpenFOAM file. So you just write the dictionary, you say, okay, the temperature. Then you say, give it a title that you want to see on top of the graph. You say, give it a label so that units are displayed on the graph so that everybody knows what the 300 thing is. And what Ignaz then usually does is he copies the output that I've shown you before. He copies it into the expr, and then he replaces the parts that he wants to scan for. For instance, the minimum temperature. He replaces it with these four things. That basically means this is a group of one or more characters. And when PyFoam finds such a group in your regular expression, it will write that out as analyzed data, and you can give titles to the groups that's in the order that they are written here. So you can tell it, okay, minimum 10%, average 90%, and maximum. Yeah, and now if you rerun with PyFoam plot runner, if you rerun it, then you see such a plot. You see the maximum temperature that is inside of that at first is quite high because of the heated plate down here, and then once the convection starts, the maximum temperature has a more steady thing. Yeah. So what what Ignaz also wants to see is the patch temperatures. So what he can do here, he adds some more function objects to the control dict. He says, okay, I'll take the temperature, I'll take everything from the other temperatures, and he does it in two different ways. Either he says, okay, instead of swak expression, I use patch expression, and please calculate it on these three patches. Or that's the temperature. Or what's even better, because if the floor has, for instance, has a maximum temperature of 600 degrees, and you've seen the graph before, that would mess up everything. So Ignaz says, okay, the patch expression should not be the temperature on the patch, but give me, with internal field, give me the values of the cells immediately above the patch. And that generates much more output, which you can see here, where you see, okay, the wall these are the interesting ones, wall temperatures internal, on, floor, and then you get the temperatures above the floor. And now he says, okay, I'm going to add a swak expression again to this, a regular expression again to this. I think I've got half an hour, so I'm going to speed up a bit. And it's a similar expression, but what he also does is he puts a group here where the boundary name is supposed to be. And then he tells PyFoam, okay, this is a dynamic plot, and you'll find the ID in the first group. And so what PyFoam then does is it analyzes it, it finds all these values, it says, okay, this is the ceiling, so I'm going to, so for the ceiling, I'm going to add a line for the 10%, for the 90%, for the average, the minimum and the maximum, and I'm going to plot this. And that way the expression, if Ignaz later adds some more patches like window or something like this, and adds it to the function objects, then they will be automatically be picked up. So, so now what Ignaz wants to do is he says, okay, I need this Fahrenheit field. I need it all the time because it's an American company. They need everything in Fahrenheit, and I want to calculate this during the run. So for instance, there's a function object that's in this library. There's a function object that's called expression field. And what expression field does is it's similar to funky set fields. You specify a field name and you specify an expression. And at the end of every time step, swak4Foam will evaluate this expression and put it into a field with this name. And every time all the results are written, then it will automatically write it to disk. Okay. Yeah. Also, until now, Ignaz used the funky set fields in the what I call the command line mode, where the expression is specified on the command line. But you can also use it in dictionary mode. The advantage is that you're more flexible, you can do more things, and basically you only have to call funky set fields only once to do multiple evaluations. And so basically what he does here is he wants to normalize the velocity inside of the room. So basically normalizing means he wants to divide it by the length or the size of the room to get a dimensionless velocity. And the thing here is he uses Lmax, a variable, and variables can be specified almost everywhere where you have a swak expression. You can also specify variables, which makes it much easier to read the things. You specify variables like this. You say, okay, there's a list, there's a variable name, and there's an expression for it, and you need a semicolon afterwards. And you can use, inside of expressions, you can use variables that were specified before, like here where he takes the maximum. And you can use any fields or any swak4Foam functions. Yeah, I'm going to skip this. This is a bit more, yeah, this is a bit more esoteric. Yeah. So, yeah, this is just one nice thing is basically if you add to PyFoam Runner, if you add cursors and if your terminal supports it, then instead of the regular output, you will get this colorful output where basically PyFoam prints out the regular output that it gets. It immediately shows you, okay, I've analyzed, for instance, I've analyzed this expression. I've got these, I've got for K, I've got this residual and these things. Down here, it plots you how many % of the time steps you already have run. You get the number of iterations that it does per second, so the number of time steps that it does per second, and it gives you an estimate how long the run will take. That's nice. Yeah, so everything Ignaz has done so far, you will find in the material to the training in 0.2 static tar gz. Now, I said Ignaz wants to move wants to investigate how moving a heater around improves the room climate. And he also wants to see the different heat fluxes on the different boundaries. So what he does is he creates a new case with Simple Groovy, which is called Simple Groovy BC. And now we add another library to the libs list, that's libgroovybc. And by adding this libgroovybc, the solver will know about a new boundary condition that is called groovybc. groovybc is also quite an old part of swak4Foam. It's basically based on the mixed boundary condition. Don't know how often that basically the mixed boundary condition is in OpenFOAM is a boundary condition where you can say, okay, either this boundary is a fixed value or it's a fixed gradient condition. And you do this by setting, usually you say, okay, you set a value fraction. And what swak4Foam does is you specify, that's optional. You can optionally specify a fraction expression, and if this fraction expression evaluates to 1, then it assumes that it's a fixed value boundary condition, and if it's evaluates to 0, then it assumes that it's a fixed gradient boundary condition. And if it's 0.5, then it assumes a mixture of the two of them. But this is optional. The gradient expression, that's basically how big the gradient should be, that is also optional, because most of the time people only want to use the value expression, and that describes the value that it should have. So what Ignaz now does is it says, okay, instead of this rectangular heater, I want to have a heater that is a circle with a diameter of 1.5 meters. The center moves around, the center of that circle moves around the room on a circle that's also 1.5. And it needs an hour to move around the room. So that's basically just the time we need for the simulation. And here Ignaz specifies, okay, he says, okay, the center of the room is this. He specifies the radius of the heater, which is half the diameter. Here he specifies the radius of the circle. Then he calculates the radiant. So basically, at which angle are we currently? He says, okay, take the current time in the simulation divided by 3600 and multiply it with 2 times p. P is defined in swak4Foam, and time is basically a function that swak4Foam gives you. Then it calculates, then it says, okay, the middle of the circle is a vector, is basically is the center plus the radius of the circle, and then it specifies a vector, and this vector is calculated from the radiant above. And what it says then is, it says, okay, if the current position on the patch minus the middle, if the magnitude of this, which means basically take the absolute value of this, if this is smaller than the radius of the fire, then use the high temperature, otherwise use the low temperature. This question mark colon syntax is something that swak4Foam borrowed from C and C++. That's the conditional operator, which basically says, evaluate this expression. If it's true, then use the first expression, otherwise use the second expression. Because this is a rather complicated boundary condition and Ignaz never gets these things right in the beginning, he uses a utility that's called replay transient boundary condition that is used to, which basically loads the temperature field and then steps the time along and updates, just tells the temperature field, please update your boundary condition and write yourself to disk, but it doesn't do the real physical simulation. And using that, you can check whether you did the boundary condition right. And now when Ignaz now runs this modified case, he gets these temperatures. You see that the temperatures are higher than in the original case, which is perfectly understandable because the area of the circle is much higher than the area of the rectangle that we had before. The wall temperatures, they are also different. And what you see here is you see the moving heater in the beginning. Yeah, and you see it moving around. So the next thing is he wants to calculate the wall flux, and for the wall flux he has to get not the wall flux, the wall heat flux. For the wall heat flux, he needs fields like the thermal conductivity, and he's not quite sure how they are named. And there is a function object in swak4Foam which is called list registered objects, and if you put that in, then swak4Foam prints out all the objects that are currently there, and basically all these objects can be used in swak4Foam expressions. So it tells us, okay, thermal conductivity is called thermal colon alpha. So Ignaz says, okay, that's the one that I will need for the wall heat flux. He also wants to know which which function objects are there. For that, you can use the banana trick. The banana trick is something that you can use for every runtime selectable thing, and probably have told you about the banana trick before. So basically, you just put in banana and you will get a list of all the function objects that are there, because it's quite a lot. So what Ignaz now does is he creates a new file that's called heat flux. He puts in, the important thing about this heat flux field is here is the boundary field, where he says, okay, for every boundary, now use a Groovy boundary condition with the value expression. And now he says, okay, kappa times the surface normal of the temperature on this patch. The variables that he uses here is CP gas, which he hard-coded to 1000. And then he uses this kappa, and there he uses alpha t. The thing is that you've seen before that the colon is used by swak expressions. So swak4Foam can't use a field with a colon in the name. So you've got to specify an alias where you say, if you find an alpha field, then an alpha t inside of your expressions, then instead use this thermal alpha thing here. I've just spotted a typo. There should be a t after the alpha here. So yeah, that's what the aliases are for. And now to get this calculated, there's another function object that's called read and update fields, which basically only needs the name of a field. And when this function object is used, then OpenFOAM loads this heat flux field that we specified before. It loads it into memory, and every time, at the end of every time step, it updates it. And if it's time to be written, then it writes it out. So the field report, now we can have a look at the heat flux on the different patches. The interesting thing here would be the weighted average. Here I explain a utility that's called funky-do-calc, but I've only got 10 more minutes, so I'm going to speed through that. That's basically a utility where you can do any kind of swak4Foam evaluation you specified in the dictionary, and you can run it after after you've run the simulation. You can, with the field that we've created, with this heat flux field that we've created, you can do all kinds of usual integrations. Here it explains how to use so-called remote variables if you want to do some things like calculate pressure differences between inlet and outlet and things like these. Then you will need these, but I'm not going to explain this. He plots the heat flux. The only new thing about this is basically he merges two plots in the custom regex. The one is the publisher, that's the plot up here, and the other one is the collector. The collector doesn't open its own plot window, but it appends its plotting here to the other plot. Okay, and there's a slightly new state file where I've used the warp with scalar filter to visualize the heat flux. So basically, the higher the heat the heat flux is, the more this patch is warped away from the geometry. And yeah, here you see it a bit later. Okay, that's all in free. So I'm going to go over the more advanced features. I'm just going to explain you what happens here approximately, and yeah, going through this. Ignaz noticed that there are jumps in the results. The thing is that we have discretization problem here that we have. Basically, we have the circle moving around, and sometimes, and the circle switches certain cell patch faces, it switches them on immediately. What we do here is, or what Ignaz does here is he plots, at first he plots the wall temperature plot before. Here you see the discretization when the circle moves around and switches on and off. And what he does here, that's a bit more complicated, he does some smoothing by interpolation. And once he does the smoothing by interpolation, you see here that the maximum temperatures are, you still see some jumps here, but they are by a factor of 3 smaller. Then Ignaz finds out, okay, there's this lumped boundary condition that's in OpenFOAM in the ESI version since 1612, which he would like to use. Basically, the lumped boundary condition for the is basically you say, okay, instead of having a zero gradient boundary condition or something like this on top, I want to have I want to simulate the whole solid. So what it does is it says, okay, I have a solid with a mass of 1000, a CP of 4100, an initial temperature of 300, and then OpenFOAM then updates this temperature over the time according to the heat flux that would go into this top. And as in the foundation release, such a thing is not there, then Ignaz decides to at the ceiling to replace the boundary condition with a groovy boundary condition, where he says, okay, use T lump, and T lump is calculated according to these things. The nice thing about this here is that he says, okay, there is a variable T lump here. That is a so-called stored variable. This variable remembers its value between each time step. So this variable is updated and stored over time, and what you see then is that the ceiling starts to heat up here. And yeah, these are the heat fluxes, they differ slightly. And the last thing that's is basically there are boundary conditions in OpenFOAM where you have external wall heat flux, where you specify an outer temperature and you specify a heat transfer coefficient. And you specify here, you specify this to be uniform. And the thing is, in normal OpenFOAM, there is no way to specify this as non-uniform, and swak4Foam has a utility for that. Let's see. Yeah, at first we use this on the regular case, and and we, yeah, there was some post-processing for this, and swak4Foam has funky set boundary field where you can specify that you say, okay, on the patch fixed walls, there is a entry that is called H, and this entry H, please evaluate this patch expression there, and then put the result into that. So basically what you can write any expression. The expression that I wrote here basically cuts out some windows, and then you have to add this right boundary subfields. You've got to add this to the case setup in order for it to be run. And what you get then there is a heat transfer coefficient that looks like this. So you get on the outer wall, you get you have the windows which have a high heat transfer coefficient, and the regular walls, which are pretty good insulated. And when you now run this and you again do a warp with the heat transfer, then you see that basically there's still a lot of heat going out through the ceiling because the hot air that is rising from the heater, but there's also a lot of heat transfer that goes out of the windows. So yeah, if you want to keep your room warm, then don't add any windows. The heat flux is wrong. There is a physical reason for this, but yeah, we're not going to go to this. And yeah, just wanted to, the cursors thing that you have, if you put in there a long progress instead of the usual progress, then basically you get this view where you can see all the values instead of, and you can have a look at exact values while the case runs. Okay, and all this is found here. So, yeah, Ignaz says goodbye. He's happy to be working with OpenFOAM again. He found a new purpose in life. He's bringing warmth to quadratic rooms, and we might hear from him again. There is more. We've only seen some parts of PyFoam and swak4Foams. It can do Lagrangian particles and other stuff. Further readings, recommended reading is these 2 pages on the OpenFOAM wiki. There is an incomplete reference guide that comes with the swak4Foam sources, where at least all the functions built into swak4Foam and the expression syntax is described. There are further presentations, one about PyFoam prepare case. There is one that's called PyFoam for the lazy, about using PyFoam to write out data. And there are several more advanced presentations about swak4Foam and a presentation programming with PyFoam that was held at the last OpenFOAM workshop. So yeah, thank you for listening. I think I'm in time. The problem is that I don't hear anything, so I will have a hard time listening to your questions. Yeah. From my side, I'm finished. If we don't find a way to go on, then I think I will conclude this, and I'm sorry for the delay and yeah. Okay, thank you.